All right, we're going to get started. Hi, everyone, and welcome to our fourth webinar of our Spring 2021 series. Just a reminder to change your name, if possible, to your name, company/university. That is mainly for the Q&A session at the end, just so it's easier to call on you. For those of you that don't know me, my name is Kelly Baber. I'm an energy systems engineer at Rutgers University. Just a reminder to keep your mics muted throughout the call. We will have the webinar followed by a 15-minute Q&A. So any questions you have, you can either type in the chat and we will address them at the end, or you can just turn your mic on at the end and ask them. Just a quick mention for our next webinar. It will focus on power reclamation of utilizing micro hydro turbines in the aeration basins of wastewater treatment plants. And that'll be later on in March. On to today's topic, the framework for net zero wastewater treatment plants, which will be presented by Sochi from the University of Illinois at Chicago. She's a master's student, and I will pass it over to you now.
All right. Hi, everybody. I'm pretty excited to be speaking to you all today. So as Kelly just mentioned, I'm going to be speaking about a framework for net zero wastewater treatment plant. I am from the University of Illinois at Chicago Industrial Assessment Center with their director, Lynn Lee, Cliff Hefke, and Patrick Brown. So I just want to start off by giving a big thank you to all three of them, and then also the rest of the IAC team for all their support and the guidance on this so far. So taking a look at our agenda, I'm going to start off by talking about a little bit of background on wastewater treatment plants. I'm going to talk about some IAC statistics on assessments that we've done. I'm also going to be talking about energy efficiency strategies first at wastewater treatment plants and energy generation considerations. And then finally, a case study that we've done here at UIC. So this is a map of wastewater treatment plant statistics. So this is a map of all the wastewater treatment plants in the US, and these dots represent the size of a wastewater treatment plant and the capacity that they exist to manage. So as you can see, we have a lot of wastewater treatment plants along urban centers, especially along the East Coast. We have a lot along the Great Lakes and around here in California and Seattle. Around the center of the US, we don't have as many wastewater treatment plants, and then also they're a lot smaller. And this is really just because we don't have a lot of people that are living there. But there's 15,000 in the US, and we are looking at energy efficiency in these wastewater treatment plants because they take up about 15 to 30% of municipal energy costs, and that's a huge portion. And collectively, they consume about 2% of electricity in the US. So we definitely are interested in looking at energy efficiency strategies for them. And one of the initiatives the Department of Energy has is working with us, the IAC programs, on giving recommendations to wastewater treatment plants. So wastewater treatment plants are actually a fairly new initiative within the IAC. Our very first wastewater treatment plant assessment, according to our database, was in 2006. So this is a map I created of all the wastewater treatment plant assessments that have been done within all the IACs since then. It looks a little different than the map we've just seen. Number one, I don't have location data and specific cities that these plants are located in, but I do have the states they're in. And it looks a little different because if you notice along the East Coast, we don't have a bunch of wastewater treatment plants along there. There's a lot in California, Arizona, Wisconsin, and Florida, though. So a lot of our data is going to be skewed towards what these plants are seeing. But nothing I'm going to note is that this map only has 158 wastewater treatment plants. And as I mentioned before, there's 15,000. So there's a lot of room for growth on looking at what kind of wastewater treatment plants we want to do assessments on. So just to make sure that we're all on the same page here on the treatment process, I'm going to walk over a very high level overview of the treatment process at a wastewater treatment plant. It's going to change depending on the specifics on the site and what their needs are, but in general, they're going to have primary treatment, secondary treatment, and tertiary treatment. So when the water first enters the site, it's pushed through screens, and a lot of the larger pieces of trash that might have been flushed down the toilet or thrown in along the pipes is going to be filtered out and put into the landfill. Next, there's going to be grit removal, which is going to get, again, a lot of larger particles like sand and glass. And again, anything that's removed there is going to be tossed to the landfill. And then finally, there is primary settling. A lot of the larger organic particles are going to settle out in this stage. And the key is reducing this as much as possible, because this organic load is what drives the energy usage in the next step in the aeration stage. And that's part of the secondary treatment. So in the aeration stage is where bacteria is processing a lot of the organic waste in the water. And then when that's done, there's a final settling process where all the rest of the organic material settles out. And then finally, there is the tertiary treatment process, and that's the disinfection. There might be some more processes in the tertiary treatment, but at the very least, you're going to see disinfection, which is going to be chlorination, dechlorination, or else UV. So alongside the water processing, there's also sludge processing. So I touched on how in the screens and the grit removal, that waste is thrown in the landfill, but the organic material that's settled out in primary and in final settling can actually be collected and used in another way and processed. So it's removed out from these two stages, and that's where it's thickened down from about 7% water down to 2% water. After it's been thickened, it's put into an anaerobic digester where it sits for somewhere between 15 to 60 days. Again, depends on the site capacity, the tank capacity, and what the site can handle. And then when that sludge is done being processed, it's dewatered. The water is pretty ammonia heavy, that's stored somewhere else on site and then fed to the head of the plant. Or and then the biosolids are then able to be sold or distributed in some other way. So these are some background statistics we have from IAC assessments we've done. This is from the 158 wastewater treatment plants assessments that I mentioned previously. So these plants range in size from about 100,000 to 10 million gallons. And as you can see, the larger the plant gets, the more electric usage they're consuming. And this is a pretty long established relationship. And it really depends on what their processes they have on site. But it is nice to have this kind of baseline to note where your site should be falling on electric usage and how far above or below this line they are. So another way to visualize that data is with the energy use intensity distribution. And this is another way of looking at it with kilowatt hours per 1,000 gallons. And as you can see, most of these sites are falling between 1, 2, or 3 EUI. But as you're getting a little bit larger, we are seeing some outliers. And again, this is just another nice baseline to have as a tool for other IACs. You know, if you are seeing a plant is falling at 7 or 8, this is a good indicator that there are some energy efficiency opportunities available that we can take advantage of, that we should be looking at to reduce before looking at any new energy generation strategies. So where is all the energy being used on this site? As you can see here, a huge portion of that is going to be in the aeration or in the secondary treatment of the stage. That's usually taking up at least 50% of the electricity usage on the site. So this is going to be a big focus when we want to look at reducing energy usage. Another big one is pumping. Of course, that's used at the beginning of the plant and then also all throughout. So the water is being pushed wherever it needs to go in order for it to be processed. So that's another huge opportunity for energy savings. And next is anaerobic digestion. Not all sites are going to have anaerobic digesters, but if they do, it's going to be a huge consumer of energy. And as we can see, belt process, clarifiers, grit, chlorination, they also use some energy, but they just don't use the massive proportions that aeration, pumping, and anaerobic digestion use. So because of this, we're taking a look at some of the top measures that IACs have done, and they are related to the largest energy consumers on the campus. So the first one we're going to talk about is aeration controls and technology. There's also pumps and motor recommendations. There's recommendations for anaerobic digester processing, also in the final tertiary phase with disinfection, and then finally lighting. So there's two main purposes of aeration. The first one is going to be mixing the wastewater, so it's uniformly distributed between the water and the bacteria and any of the pollutants in the solution. And then the second purpose is to expose the water to oxygen, and this really keeps the bacteria happy, so they can continue processing the water efficiently. So the first type of technology is mechanical aeration, and that's going to physically be pushing the water towards the surface to expose it to oxygen there. And this has some limitations, like if you've ever seen a blender and you're trying to make a smoothie, and there's also like always some parts of your blender where the blades aren't really reaching. So the mixing is really efficient on the site where the blades are, but it isn't always completely uniform all throughout. And there are some limitations on the depth of the tank that this is going to work in. So there's also coarse bubble and fine bubble aeration. So coarse bubble has much larger bubbles. And so because they're so large, they're gonna move through the solution quickly, and this is gonna do a great job of mixing. But it's not gonna have a very high oxygen transfer efficiency, which, as I mentioned, the bacteria need to be kept happy and process the organics. And then finally, there's fine bubble aeration, which is by and far the most energy efficient aeration technology available. It's not going to offer the mixing benefits that the other two might, but it has a really, really high oxygen transfer efficiency, which is going to be great for the bacteria processing in the aeration process. Another thing to look at in the secondary treatment stage is the aeration controls. There's a lot of really extreme and a lot of really rapid load fluctuations in a wastewater treatment plant. And so this could double in just a few hours time. So not being able to control for these rapid fluctuations can cause excess energy consumption of 50 to 65%, which is just massive, especially when you consider that this is the largest energy consumer on the entire campus. And so one way to do this, to account for this, is to calculate the ideal operational DO rate. This is the dissolved oxygen rate. And this really depends on the uptake of the oxygen in the bacteria on the site. So you can monitor in real time the amount of water that's coming in, the pollutant levels that are coming in, and you want to make sure that you have a way to quickly respond to all these fluctuations and quickly respond with the DO rate and aeration levels. Another thing to look at is in pumps and motors. So starting off more in like the design phase of the system, very first thing to look at is system head reduction, and that's really just the height that needs to be pumped. So ideally in a wastewater treatment plant, you want to start the process as high as possible, and then gravity can really be doing most of the work for you. You are still going to require some pumps along the way, but having gravity do as much work as possible is going to be really helpful in energy efficiency. Another thing to look at is VSDs. Just like with the aeration process, there is, again, a huge change in the amount of water that might be coming in. And so you want to be able to respond directly as these changes are happening with the capacity on your pumps and motors. And then next you can look at pump size. We've seen a lot of oversized pumps and undersized pumps, and so it's really important to look at a pump that's going to be operating as close as possible to manufacturer requirements. And then finally, we can look at SCADA, which is a supervisory control and data acquisition system. And so this is a pretty comprehensive system, especially really helpful on a wastewater treatment plant because of these rapid fluctuations that I keep mentioning. And so it's important to be able to respond in real time, because if you're moving too slowly on those response times, or you're not getting accurate data, that's going to be probably the biggest things for your energy use. Next, there's disinfection, and this is, again, the tertiary treatment process. There has been a lot of movement from chlorination towards UV. Even though chlorination doesn't use a lot of energy, there is a lot of environmental concerns. So we are looking more and more at UV systems. And these ones can be tough just because there are effluent guidelines with how many pollutants and viruses and what can be coming out of the water. So it's pretty difficult to do, but you need to make sure that you are considering them and mentioning them in making this recommendation. So you can monitor the disinfection requirements based on the flow of water that's coming in at the plant at the time, or based on the pollutant rate that's coming in. And so again, you're going to need to monitor these in real time. So there is the least intense UV lamp is going to be a low pressure, low output that comes out at 88 watts and lasts relatively long at about 13,000 hours. Moving to a little bit more powerful, there are low pressure, high output, and these might cost a little more, and they are a little more energy intensive, and they might not last as long, but a lot fewer of them are required compared to an LPLO lamp. And then finally, there is a medium pressure, high output, and that uses about 10 times more energy and lasts about 8,000 hours. But this has the fewest lamps required. So it really depends on the site requirement, which is going to work best for them. And then finally, a recommendation that we're probably all very familiar with. This is applicable to pretty much any site you go to, wanting to use the most efficient lights as possible in their buildings and throughout the campus. So this is a table of just 5 different lights, and you can see along the way that their LED equivalent is uses a lot less energy than the older ones. And so not only are they less intense on their power, they also have a much longer rated lifespans, so you can save money on buying new equipment or on replacing them. And they also can operate at more extreme temperatures. I mean, that's always a perk when you're living in the Midwest and we have really hot days and really cold days. LED lamps also can start instantly, so there's no warm up required like you might see on older light bulbs. And then also they can be used with lighting controls. And so this is another perk on a wastewater treatment plant campus, just because there are lots of buildings on campus and not all of them are being used all the time. They don't have a huge staff. So someone might be coming in to operate, look at a motor for a little while, and then they might be leaving. And so you want to make sure that these lights aren't just being left on 24/7. So it's really nice that they're able to be compatible with these lighting controls. And then this is a new technology. It's pretty difficult to recommend just because we haven't seen a ton of these available yet in the US, but I did want to put it on everyone's radar. So I did talk a little bit earlier on about how the dewatered sludge from the anaerobic digestion process is really ammonia heavy. And this is really what's driving a lot of the energy usage in the aeration stage. So when it's fed back to the head of the plant, you're really just feeding these extremely heavy ammonia water. And so instead of feeding it to the head of the plant with those high ammonia rates, there is a new technology that kind of requires its own process. It has its own blowers, it has its own new bacteria and its own place on site. But you can recover that ammonia and then feed it back to the head of the plant with those lower ammonia rates, which is going to significantly decrease the amount of energy required in the aeration portion on site. So now that we have made this plant as efficient as possible, that's when we can start looking at energy generation strategies. So I have here combined heat and power, solar PV, wind energy, and a hydro turbine. The reason we have to be able to talk about all 4 of these at once is because when we're integrating renewable energy onto the site, we want to be able to have that energy and security. So just looking at one of them, we're not going to have that kind of security. So we want to be able to have kind of backups in case, you know, the combined heat and power system is under maintenance or the solar PV isn't offering all the electricity we need at the time. So I'm not sure how familiar all of you are with CHP. So I'm just going to do a quick overview of what that is. It's a form of distributed generation, which some people like to call microgrids, but basically you have a prime mover located on the campus, and that's generating electricity and thermal needs. So traditionally, the site is going to be pulling electricity from the grid, and then any thermal needs are being used in a boiler using natural gas. But in a CHP system, we have our own prime mover that's generating electricity, and then any of the waste heat is also being able to be used. So it ends up coming to much higher efficiencies. And that waste heat can be used for anything that's needed on campus, whether it's HVAC or in the case of wastewater treatment plant, anaerobic digesters are really the largest thermal users. So this is really efficient, clean, and reliable, affordable energy. This is a schematic of CHP specifically in a wastewater treatment plant. So as you can see here, this is our digester. It's producing biogas. This methane is being fed into the engine that's generating electricity on site. And then that waste heat is given to a heat exchanger that can go out and serve any plant needs. But also back here, it's going to heat the digester, which is then going to produce more biogas. So ideally, we're going to want to maximize the biogas production as much as possible so we can get as much electricity as possible to serve our site. The temperature of your digester is really going to depend on your site and your outputs that you want. So there's 2 different main types of digestion. There's mesophilic and there's thermophilic. Mesophilic is a little bit cooler at 35 to 39 degrees Celsius or 95 to 102 degrees Fahrenheit. So this has lower biogas production, and it also produces it at a much lower rate, but it also has much lower energy requirements simply because it's at a lower temperature. And it produces class B biosolids. And thermophilic is 50 to 65 degrees Celsius, which is significantly hotter. But it also does produce a lot more biogas at a much faster rate, but it does require a lot more energy just because it is at a higher temperature. And this produces class A biosolids. And so these biosolids are able to be sold and distributed for crops. You can give them to consumers, and so potentially this could be a higher revenue source. But for class B biosolids, you need a special permit to use those. And so really they're not normally selling them out, so it wouldn't be a revenue source for these sites. But even within one class of digestion, you still have a lot of opportunity for maximizing on that biogas production. So you say that your site had the anaerobic digester sitting at 35 degrees Celsius. If you have enough waste heat to raise that temperature by 1 or 2 degrees, you can actually increase the biogas production by maybe 15–20%, as we've seen in some of the assessments we've done. And so this is going to increase the biogas production, so you have more fuel for your CHP prime mover, and then that waste heat can then be fed back to the anaerobic digester to maintain it at that slightly higher temperature. So it's kind of nice to have that cool positive feedback loop there. Another way to make sure that your anaerobic digester is operating as efficiently as possible and creating as much biogas as possible is looking at the mixing efficiencies. So just like in the aerobic digestion part, anaerobic digestion does also require pretty uniform, consistent mixing. So there's a couple of cool mixing technologies. There's one here I'm looking at is jet mix pump system. And so these have pretty high power that they require, but they only need to be operated every 4 to 6 hours. And so whatever the interval time that the site has chosen is going to eject out these jet streams of water, which is going to use the shape of the tank to mix the water consistently. But this is another cool technology, which is just a mechanical mixer. And these have a much lower power that they require, but they have to be operated 24/7. I haven't seen any trouble with biogas production or mixing efficiencies, switching between the two, but it's really going to depend on the site needs here. Another way to maximize on biogas production was integrating in a fat, oil, and grease system. This obviously depends on how much fat, oil, and grease that you're bringing in, but it could double it or more on your biogas production. So there's a couple different considerations when you're integrating this into your site, but you want to have to look at the industrial facilities. It might be hospitals or restaurants or agricultural sites, because these are all going to have different feedstock sources with different organic materials and different organic makeups. And keeping these consistent is going to be key for integrating biogas in your site, just to make sure that you are feeding the same quality biogas into your CHP prime mover. In addition, there might be some drop-off opportunities where people will pay you for them to come drop off and dispose of their restaurant fat, oil, and grease waste. But if this isn't available, there's also some sites that have done pickup where they personally drive out and pick up in their trucks a facility's waste. So that would just be an added capital cost of collecting with those trucks. And then it's important to know how much fat, oil, and grease is going to be come in, so you know how to size your digesters. There's nothing worse than having all this waste that you can't process. It's just kind of sitting there. Another energy generation strategy is with solar PVs. And so this is unique to wastewater treatment plants because they do have pretty nice sites for opportunities here. Most of the buildings are pretty short. They're not going to be like high rises at wastewater treatment plants. So there's no buildings that are blocking the sun. And there are often pretty wide open areas. And this is a cool picture here from it's a plant in Australia. But there are basically tanks that you can put the PV cells on. And so this isn't going to affect the treatment process at all, but it is basically like free space for the PV cells, which can help with the sizing. And one of the biggest considerations with financing economics, though, and so no one's going to be investing in these PV cells if they're really not going to be paying off in a reasonable time frame. So one option to look at is power purchase agreements, where somebody else will be owning the PV cells but can sell the electricity back to the plant. And then another big one is with incentives. We especially want to look at these before they start going away. If they have them on the city level and the local level, state or federal level. So taking a look at incentives is probably going to be one of the biggest ways of getting a great payback on solar PV cells. And then, of course, I'm sure you guys are thinking the best way to have great payoff on your PV cells is the amount of production that solar PV can produce. So our friends here in California and Arizona and New Mexico are probably pretty familiar with PV just because you can get so much electricity out of it each year. We're over here in Chicago, so we're not getting an immense amount of electricity each year, but we still are actually seeing pretty great paybacks on PV cells. We are seeing a lot of investment in PV, and that's because of what I mentioned before, is we're really focusing on these incentives. Another great energy generation strategy is wind turbines. There's two different types of wind turbines. There's mechanical and there's electric. So mechanical wind turbines are basically windmills. They have to be located directly above whatever water is being pumped, and then they translate that wind energy into pumping energy for the plant. And then the other type of wind turbine is maybe one that you've seen when you're driving through cornfields, but those are electric wind turbines, and those can translate the wind energy into electricity. And the nice part about these is that these are not required to be directly above whatever water is being pumped. They can be located anywhere on the site that is getting the most wind energy. Another thing to note is that electricity production is proportional to the cube of wind speed. So that's definitely important for sizing. You want them to be operating at their maximum efficiency as often as possible. The location and the flow are really going to be what determine whether it's going to be economical for these turbines to be on site. Especially if you look here in these middle states where you're looking at Nebraska and Kansas. So these are where you're seeing the greatest wind speeds and where we're going to get the most energy from a wind turbine. And if you remember from the beginning, the wastewater treatment plants were a lot smaller there. So just a couple of wind turbines here might be a great investment because they are going to be accounting for a huge portion of the electricity usage on site. And they also, since they're so much smaller, might not have anaerobic digestion available and aren't able to get the huge portions of energy from a CHP system. Another energy generation strategy is a hydro microturbine, which apparently the next webinar is going to dive in a little bit more deeper for us. But this is pretty much a very natural way of finding energy on a wastewater treatment plant site because it is derived from water flow. And as long as we're processing water, we have that water flow. So it's a very secure, it's reliable, and it's a constant source of energy on a wastewater treatment plant site. The biggest considerations here are going to be the flow rate and the system head pressure, which is just the height that is going to be falling on this turbine. So I have here a graph of the height of the turbine, and then as you can see, as it gets higher, the amount of power output significantly increases. So similar to the wind turbines, this is most suitable for a smaller, medium-sized plant, just because it's going to be producing a lot larger portion of the electricity for these smaller to medium-sized plants. We are a little bit constrained here. If you notice, even the highest power ones are only just a little less than 30 kilowatts. So one of the sites that we visited was the Kishwaukee Water Reclamation District. This is in north central Illinois, and they were a big inspiration for this project. We've done a lot of work with them, and so I wanted to highlight some of the reasons why they've been so successful. So one of the first things is they started by looking at energy efficiency. They focused on having the most energy efficient equipment as possible. They took a look at their disinfection and chose the UV lamps that were most efficient for them. Another major thing for them was the energy management information system. So they invested a lot of time and money in understanding their energy usage and where it goes. And that's really the first step to reducing energy consumption is understanding where it's being wasted. And then on the energy efficiency side, they also engaged with us, the IACs. So even though they had really great management, they have really great expertise on site, it's also really nice to get that outside expertise and that outside insight, and maybe someone might see something that you didn't see the first time. And then after energy efficiency, they also had a lot of really cool energy generation strategies. So they had one combined heat and power system, and then they were planning on integrating a second one down the line. They have plans for solar PV cells, and they also have plans for a hydro turbine. So again, they focus on having this redundancy, this energy security, and this resiliency with multiple energy generation strategies. So again, the pillars that I want to focus on for their success was first their energy management, understanding where it's going, and then reducing that as much as possible. Another one is going to be investment, understanding what is the cost of these technologies and what is the payback, and being willing to make those investments. And then finally, another reason for their success was program engagement. So not only with the IACs, but they were very vocal within their communities. They always were wanting to show off some of the work they were doing and know about the different resources available to them. And so another thing we partnered with them on was in this Kishwaukee Water Resource Recovery Prize. So our office, they didn't only engage with their IAC, they looked at a lot of other Department of Energy programs that were available to them. So we were really, really excited to partner with them for this. And we are so glad that they were awarded this, and they were awarded $50,000 from the Department of Energy. So I really want to stress the importance of wastewater treatment plants partnering not only with the IACs, but everything that's available to them from the Department of Energy. So I think as IAC students, we have a lot of responsibility and a lot of resources available to offer to the sites so that we can advance the energy security and the efficiency in the US. Thank you. Are there any questions from anyone?
Thanks, Sochi. So we're going to go into the Q&A. So if you have any questions, you can just turn your mic and video on if you can, or you can put it in the chat and I will read it for you. All right, so we have one from the chat. So what is the minimum plant size for an anaerobic digester?
I'm not sure on the minimum plant size for an anaerobic digester. I do know that the minimum plant size for a combined heat and power system to generally be economically feasible is going to be 1 MGD, or 1 million gallon per day.
All right. A question about the recording. Yes, this webinar will be put up on our public webinars page, which is iac.university/webinars. Another question from the chat. Do you know how many of the wastewater treatment plants that have been assessed by the IACs have anaerobic digesters?
No, we don't have information on that, unfortunately.
We have more. Wouldn't a micro hydro turbine compete with the pumping energy requirements? Or are you locating at the end of the process to take advantage of gravity drop?
So generally when you're integrating in the micro hydro turbine, you're putting it in wherever you're naturally having a gravity drop anyway. So it's not really going to compete with any pumping requirements.
All right, do you have some more questions? Okay, another one from the chat. Do CHP systems ever use turbines rather than piston engines for generation?
You can, and it is fairly common, but within wastewater treatment plants, most are reciprocating engines. This is just because they are a lot more forgiving to the abuse that biogas is going to have on the system compared to a micro turbine or a steam turbine. Those also require pressurized gas, and so it costs a lot more on the capital cost of buying compressor equipment for that biogas, just because it's not naturally going to be pressurized like natural gas might be.
All right. Just so you know, you can also unmute yourself if you prefer to ask yourself. Another question: did you come up with did you come up with specific recommendations on how to use the blowers more efficiently for aeration and how much energy that would save?
Yeah, so that again really depends on the site. We have recommended more efficient blowers to a site, and so that one, it really depends how much electricity is going to save based on the site. So I can't give like overall concrete numbers on that. But yeah, there are recommendations on high efficiency blowers, having VFDs on your blowers, and just making sure that you are operating at the optimal DO rate for your site.
Okay, I missed one earlier in the chat. We have observed long, simple payback periods when we suggest the use of digesters. What aspects of a digester should be focused on when recommending one?
Yeah, there's a few different factors there. You're going to want to make sure that you're looking at the size of the digester would be most important. So having like an oversized or undersized digester is going to affect the number one biogas production rate, and then also the mixing efficiencies. So looking at the two different mixing technologies I mentioned, this mix pump mixer is going to be able to efficiently mix even if the digester isn't completely full, while this mechanical mixer doesn't mix as well with different volumes of the digester. So the main one is really looking at the anaerobic digester size, and then also how much is going to be exposed to the air for ensuring that heat retention as well.
All right, thanks. Another one. What changes to the anaerobic system are needed to change from MESA to thermophilic bugs?
So really the main change is on the temperature. They have two completely different types of bacteria, and it is going to take some time if you want to transition from one to the other to let that bacteria like slowly grow. Another thing that I didn't mention previously is that if you have enough thermal energy to keep your digester at 45 degrees, it's not going to be beneficial for you just because the mesophilic bacteria is not going to be thriving and the thermophilic bacteria is not going to be thriving. So it's not going to be producing the biogas that you want. You have to commit to one or the other. And so really it's going to be related to how long it takes that bacteria to grow.
Another one from the chat. Is there a reliable source to estimate the cost for a digester?
Not that I know of. I think that it's pretty difficult to make exact recommendations on that because it is so dependent on the site.
Hey, can I go with a follow-up on the MESA and thermophilic bugs? On that one, hey, so if you switch around, you're going to get higher energy production, which I'll assume means a higher percentage of methane coming off of the digester. Okay. Do you have to make changes to the CHP system to accept a higher percentage of methane in the system?
No. So the biogas is being well. So you do need to make sure that the quality of the biogas being fed in is fairly consistent. But whether you're in mesophilic or thermophilic, the biogas that's being created is being treated. And so that's more on the treatment end of things, but it's not going to be affected by like the quantity of the biogas that your system is creating.
All right, thank you.
All right, another one from the chat. Is biogas being used for the energy production of the site itself, or is it being sold for revenue?
So that depends on how much you're producing. Usually you're not producing more than the site is using, so it's all being used on site. The Kishwaukee site that we visited actually was producing so much biogas that they were purchasing another CHP system, which would make more electricity than they were actually using. And so one of the perks of staying connected to the grid is that you can sell that back to the utility. So that's absolutely something that can be done.
Okay, thanks. Another one. What is the ideal DO concentration for aeration, and do the plants that you have visited stick to this ideal concentration in general?
I don't know the exact rate. Sometimes it's pretty difficult to get information from a plant manager on their exact values of DO rate. So this is really more of like a luck thing if you can get that information from them. A lot of times they don't even know. So it is just something to take note of because it is a pretty significant indicator of energy usage.
All right. Were there any issues with the data you used to compile the IAC statistics you showed at the beginning, like the EUI graph?
Yeah, so actually, all the wastewater treatment plants we've done, according to the database, I think there was like 218 of them, and then I narrowed this down to 158. Number one, there were a lot of different inputs on the units of water being processed. So I stuck to only the ones that had thousands of gallons, but there were some that just said units. There were some that were outside the realm of reality. Like one of them said that the wastewater treatment plant processed more water than the largest wastewater treatment plant in the world. And so you have to eliminate some of those points. And then some of the ones sitting on either end of the spectrum, there was one that had 1 MGD processed per year, or 1,000 gallons processed per year or something. And then the energy usage out that one was just completely outlying of what was reasonable for that. So it did take a lot of processing the information. There was some issues with it, but I understand how difficult it is to get reliable information from plants, especially when we're just asking for estimates. It is hard to get exact values from them.
All right.
A follow-up to that question about the problems that you had with the data in the IAC reports. You could probably get information from the EPA regions about the capacity of the different plants.
Yeah, so there is definitely a lot of information available from the EPA, but a lot of the tracking for wastewater treatment plants is done on a state level based on their electric usage and their flows. So it is just a big process to have to go through each state's EPA and pull data from that. There is some data available on the federal EPA level though.
All right. Do you have any other questions? Oh, we have another one. Was dissolved oxygen used as a VFD control parameter?
Yeah, that is. Yep. That is one of the major consumers of energy is in the aeration that's driven by the DO, right? As that's can be one of the ways that they are controlling.
All right. Any more questions? All right. If not, thank you, Sochi, for your presentation. If anyone has any more questions, I believe Sochi has her email at the end of this. If you want to put that up real quick. Any other questions, you can either email me and I'll forward it to Sochi, or you can email Sochi directly. Thank you for your presentation.